Sounds great. So we're excited to be here and talk a bit about maybe not the most usual topic regarding engineering training, but we specifically want to talk about a few things that we've seen and we'll introduce and all that, but about how you can kind of accelerate and different tips or tricks that we've picked up along the way during mostly an operations training background about how you can instill some of this operations sense to process engineers. So before jumping into it, I'll let Don go ahead.
So hi, my name is Don Glazer. I'm a chemical engineer, as is Matt. My BS is from Lafayette College. I'm the Vice President of Simulation Solutions Skills Division. Formerly had been the founder of Simulation Solutions, and my entire career has been involved in operator training, engineering training, and so on since 1974. So very happy to be here.
Sure. And as I said, I'm Matt and graduated slightly after Don in 2014 from Rutgers. And during that time, mostly what I do is operator troubleshooting courses. So I get a chance to go with Don on site and conduct these courses. And during this last year, the specific topic we'll talk about is kind of really near and dear to me because recently launched this product. We won't be talking about today, but the background's important. Virtual unit operations, we call it. And mainly what I'm doing is working directly with chemical engineering departments, specifically the faculty, and kind of tackling this problem of how do you still approach hands-on training at the education level during remote learning. So we've had some success there, about 30, 35 schools now using this package, and it's connected me a lot more to actually engineering training at the education level. So that's some background on that. And as far as our agenda today, so we'll keep our spiel here to, hopefully 35, 40 minutes or so. I'll just give a little bit of background. Why are we talking about this? Why does this need even exist in industry? So I think to give just a little color to that, I can explain kind of what I've picked up the last few years working with the chemical engineering undergraduate education. I'll say chemical engineering, and I can speak to that a lot more confidently. I suppose the folks sitting in the room that maybe went through a mechanical or even a more specified engineering degree, I would assume it's similar, but I'll talk on chemical more than anything else because that's what I know and have experience with. Then the more exciting part is we want to show you a couple different ways that you yourselves could structure exercises at your site and how you could tackle this kind of overall goal of basically accelerating the time where an engineer is able to have some more of that operation sense that, let's say, they don't walk into the plant with. We'll do that by showing 3 different snippets of exercises, kind of just enough about how you could take this and kind of really focus on, number one, knowledge transfer from senior engineers or operators even at the plant, how you could instill that into the young chemies or young engineers, I should say. We'll show this real brief demo of a troubleshooting methodology that you could take with you as soon as you leave here and maybe take something from that, and we'll kind of outline how that works. And also some methods we've taken when doing early career engineer training about trying to instill some of this practicality to control, to try to confront that age-old problem that we see with the operators, that some folks love the advanced process control and other operators like to turn it off as soon as the engineer leaves the room. So we can kind of talk about a bit how we confront that. And like I said, we'll try to take 40 minutes, no more than that, and then we'll get to kind of some possible next steps, recap, and of course the questions and answers. Appreciate Clay monitoring the chat for those as well. So in addition to an agenda, I thought this was important putting this together is to kind of clearly define the objective. And I guess to define that, first I'll tell you what our objective is not. And the objective of this is not to come here and convince the participants that your process engineers need the same level and exposure on topics such as operations or troubleshooting that a console or even field operator would. It's our contention that really to identify a few of these best practices that you can take, and really what we're looking for is to kind of minimize that time, or in other words, accelerate the ability for an early career engineer to kind of gain some of this operation sense. So it's not trying to take an engineer and turn them into an operator, but we've dealt enough with operations that, not at every site, but at some sites, there's kind of this negative feeling about process engineers, specifically early career process engineers. And me personally being on the other side of that, I think process engineers walk into a facility and you're not very confident. You're almost sometimes embarrassed about how little you know about operations. So if we could kind of give a few tips on maybe how to actually close that gap or accelerate the knowledge. That's our overall objective here today. So I'll just give a little background, and this may be of interest, and I guess the overall point really I'll come to, but just a minute or two here on the current state of chemical engineering education. And let me say that, and this is the slide with the most text in the whole thing, but let me say that working with these chemical engineering departments, you run into a lot of really kind of fabulous faculty. Some that have industry background, that's rare, but the folks that do really seem to implement a lot of experience from their site, a lot of kind of just operations, but unfortunately that's probably an outlier. The classes that you would expect to kind of cover the operations or things that would be most applicable the moment you walked onto a site, those would probably be called unit operations and process control. And I really don't want to be negative here, where this isn't a knock on departments, it's simply stating a reality. That in this unit operations class, where an undergraduate student is meant to get hands-on time on equipment, really what this turns into is, 14 weeks, you're running through 5 to 7 experiments, maybe a few more. Class sizes get bigger and bigger every year, and there's only one pump system, right? So there's not all that much time for a student actually to really get their hands on the equipment. And in addition to that, this equipment is expensive, the raw materials are expensive. So working closely with these universities, what I'm finding is the experiments are very canned. It's very kind of like you got bumper rails up there, and you're really just following this very canned experiment without much time for exploration. And again, it's not a negative from the chemie side, but it's a negative when it comes to operations knowledge. The focus on that class, more often than not, really turns into data analysis. So just to give kind of an example, when different universities couldn't get into the lab, well, what they did for unit operations this course, they simply would just provide students with data. And that was still seen as sufficient because the overall goal, or one of the goals of this class, is to be able to perform data analysis. And when I heard that, right there, it's like, okay, so we don't actually care about operating the equipment or getting the data. We just want you to be able to draw a pump curve, do a McCabe-Feely diagram, whatever it might be. So you can glean from this that going through this 1 3-credit course, there probably isn't much time to actually get some operations experience. And the second that you would point to would be a process control course. And having an opportunity the last 4 or 5 years to present with Don at AICHE, American Institute of Chemical Engineers, at the education sector for that, process control comes up every year about how the class has become too theoretical, how it's just basically another math class where you're doing Laplace transforms and you're investigating stability, which is really good to develop a critical thinker and someone that's really able to analyze data again and look at a system. But when it comes to actually implementing control schemes and things of that matter that you might do in industry, there's very little opportunity. And the last thing I'll say is just because me and Don sit on the ABET board for the U.S. Military Academy, and we get to sit through those painful meetings, is even here, the outcomes of the accrediting body, this was only added in 2012 here, these words, public health and safety. So there really isn't this main focus on safety just due to the volume of content that needs to be covered. And this paper just came out last month down at Texas A&M at the Mary Kay O'Connor Center. And it's a really interesting article, I linked it. But the last thing I'll say about the undergraduate and where your engineers are coming from is there is starting to grow a dedicated process safety course. And A&M probably does this better but I could confidently say they do this better than anyone in the country. But the problem is less than 25% of undergraduate programs have a dedicated process safety course, and even fewer make it required. So what happens is process safety is told to be spread across the curriculum, but then how do you steal time from design or control or whatever it might be? And just one quote coming from this article from last month's Mary Kay O'Connor newsletter is, you have these generations of students that graduate since Bhopal, when process safety really became a big focal point at the undergraduate level. But there's not often funding for this. There's not often research at it, so that your new generation of professors hadn't gone through process safety in depth. So then it's just this kind of continuous circle. And that was one of the main points of the article. And when we send this out, it really is a quite interesting article. So that's kind of the status as it is. So this is, okay, so how does an engineer get operations experience? Well, they get it on the job, right? They develop and they eventually talk to enough operations folks or process senior engineers, and eventually that will be kind of through osmosis, they'll get it. So what we'd like to show, and a lot of this is what Don's worked on, for the majority of his career, is just a couple different exercises. And we'll start here with, we're calling a cause and effects matrix, the style of exercise, and we'll explain how you can do it pen and paper. Probably something you've seen before. So what we want to do is explain this exercise, but then specifically call out a point where you could use a matrix like this to really kind of add on some of that operations knowledge for your early career engineers. So for the next 3 mini exercises here, we'll just use a simulated distillation plan as a basis for discussion. Very well could just be your plant, right? Using your PFDs, your DCS schematics, whatever you might have handy. And when we would typically present this exercise, and you've probably seen these before, sometimes called what if, whatever it might be, but you look at a system and you pose a question, right? So how would the following instruments respond dynamically if we increase feed flow to a distillation column? And when you go in, if I actually just cycle through, many folks will be able to tell you, well, if I put more feed flow into this distillation column, I'll actually bring it up in a second. You're going to have a higher bottoms level because you're putting more feed in. It's on control. It'll come back. I put more mass in. More mass will come out the bottom. I'm going to make my mass balance. I'll have more flow out the bottom, as well as my bottom's temperature will decrease, come back because it's on control, and I'll have to be put more steam to my heating element, here a reboiler, to make my energy balance. So when we go course to course, and I shouldn't say everyone understands this, but for the purpose of this, let's say those are answers that should be pretty similar across any distillation column that's temperature controlled. So there's a way to learn that, right? One question, so if we actually, and I'll pull up the simulator that I'll use for the demo in a second, but one of these variables, so what happens to your bottom's purity? So if you're running a simple binary column, I'll pull it up with kind of this question mark on the bottom's purity, which will be the basis for the exercise. But if I were just to pull up a rather simple binary column, so you've got a binary feed coming in, let's just call them light and heavy. If you're interested, it's C5 and C6. Feed comes in under flow control, enters the column at 95 degrees. You can see we're controlling the bottom's temperature right now at 154 degrees. That is controlling the control valve here, which is going to admit more or less steam to the reboiler in order to maintain our target temperature. The variable of interest is AI110, which is a measurement online of your percentage of heavies, or simply your purity at the bottom as a measure of heavy C6, etc. So one thing that we'll find, and I'll kind of give the basis for this, is when we go and maybe do training course for operators, we might get different answers depending on the site we're at. Some may, well, and I'll actually pose a question, see if we get some feedback. But we'll get a variety of answers for this, what will happen to this purity, let's say long term if we increase feed in. And working with enough operators, you realize it could depend on a lot of things. And I'll get more into it, but it could depend on the size of the increase. It could depend on the efficiency of equipment. It could depend on the tower capacity, et cetera. And this, I think, is such a great idea or a great example of how does an engineer coming out of university that's recently hired, how are they to learn this knowledge? Other than just studying their specific unit, but even then, if we're talking inefficiencies, if we're talking, well, it depends on this, it depends on that, that's that knowledge that's very difficult. For example, if I were to increase the feed flow, and I'll just do it now, and actually run the simulator. And then I will pause and see if I can open a poll, get some feedback. But to call out some of these variables, if all of a sudden now I'm putting more flow in, now we see our levels building. Well, that should be true, right? And that's covered in mass balance, a second semester course you take at the engineering level. The course your level is going to build because you're putting more flow into a fixed tank. And then you take a control course, you understand how a control loop works, you understand mass balance, you're pretty confident that if the only change you make is increasing feed flow, your bottom's product flow is going to increase. And you could come in and, trend this, and everyone's happy here. So the issue with AI110, as we see our temperatures dropping, TIC 100, So we put more cold feed in, right? It enters the column around 95. Extra of that volume is going to cool down the bottom, slump the reboiler temporarily. Dark blue is my temperature. Eventually, it's going to come around because it's on control. And how is it going to come around? We're going to add more steam. So the question I'll pose, and I'll actually see, I'll open a poll. So if you're familiar with WebEx, a poll just popped up on your screen, and you can move it around. It's yours to manipulate. You can actually, if you want to, and it's all anonymous. It's all anonymous. You could just click an answer and hit submit. I'll see if we get a couple answers in here. But the idea is, the question being posed is, if we increase the feed flow to this tower, and I know you've looked at it for all of 6 minutes now, so you should be experts. But if we're on temperature control here, what's the prediction about what would happen to this product purity? AI 110. So if we were normally running at I'll kind of give you a hint. We were normally running at a 92.4 split, whatever it might be. And I can at least give you the beginning of it. So we haven't settled out yet. I'll reveal that. But we see we initially drop in purity. So typically in a class, we pause and take, 15 minutes and have everyone predict. But if you do want to make some predictions, I see them coming in, so I appreciate there's quite a few coming in. So I'll pause just for another second. But I just want to highlight this one variable in this case, rather than look at the system, to really kind of hopefully drive this point home. You can see our TIC 100 is about back to our normal temperature. So let's assume at the end of the day, we get back to our normal operating temperature, normal operating pressure, feed composition hasn't changed, we're just putting more volume of it in. Great. So I'm going to go ahead and, just for the sake of time, close the poll. And what I'll do is I'll share the results back with you. And this is what we typically do in a class. Well, what you'll see as I continue to run this, I'll kind of jump ahead before I share the results. And they're varied, as they, in this case, should be, because there are multiple answers. Is AI 110 long term? If I were to trend this and let it run and settle out, and in this specific column, we'll cycle around, but we'll actually end up lower. Your purity will drop. Specifically, here, I'll share results. Just so you know, when I share results, so I'm going to do that right now, you're going to get a window that's going to pop out up in your main screen. That's yours to manipulate and yours to exit out. So after you look at the results, if you want to get rid of it, it's not coming from the host. That's up to you to exit out when you're ready. But the whole kind of point of what we're talking about here is, for this one specific variable, here's the long-term response from the simulator. And in our case, even if you maintain bottom temperature, long-term, you won't get to the same purity. And if you were taking a separations course, you would be told, because again, it's all in theory, that if you maintain your overhead pressure, overhead operating temperature, and your flow characteristics on the feed do not change, then you should be able to return to the same purity. But of course, in real life, there's a lot of different things that are going on here. The reason it might not return, well, perhaps you have too much volume in your tower, right? And all of a sudden you have some sort of flooding or entrainment. Maybe there's inefficiencies in your reboiler or your preheater due to the extra flow. In a more extreme case, maybe the controller was left in manual, so it never maintained. Therefore, your product purity never got back to where it was. In our case, it happens to be the inefficient trays. But the point being is that this isn't something particularly, unless you go over the scenario, that is really focused on at the education level. So an engineer might be resorting back to what should happen rather than what will happen in this system. And I think this is just one of those highlighted scenarios from our courses and things we do, that we see there's always different answers, and the operators can confidently tell us why it's going this way or that way. And there's always this, well, our reboiler can only handle so much flow, or we're running our tower as much volume as we can. And I think those are some of the challenges. And so our key takeaway here is understanding these specific system responses related to equipment efficiency or upper or lower bounds. That's that operations knowledge that doesn't come overnight. That's that, well, Joe has been at the plant for 20 years. He knows how that crude unit runs like this. And why is that? Because he's seen a lot of these different things. And how do you accelerate that knowledge? One solution that's worked rather well for us is, and this is something you can just take, there's nothing scientific about this. I think the why is the biggest point, is creating these flow charts where you pick the change you want to do. And now this isn't theoretical, this is from your unit. And what you do is you have the different answers here, but the most important thing is this why. And again, we're not reinventing the wheel here, but I think there's often a gap in the loop here where having an experienced engineer or having an experienced console operator write in plain text for this system, given this one change, here are how the variables will change, And AI 110, well, theoretically, the composition should get back to the certain specification. In this case, it won't because of the extra flow in the system or whatever it might be, right? So again, this is just one thing we've done where if you can get that synergy between operations and have documentation for early career engineers, we've seen sites that have done this, and the benefits, I think it just instills a bit of that confidence to the engineers.
Did you want to share the format?
Yeah, I shared.
Okay.
Yeah, we had, I should give some credence to that. Majority of the folks that decrease and increase. So get less pure and then come back, which is theoretically the best answer. And if your column has the sizing, that's probably most commonly what will happen because you probably aren't running at the edge. So yeah, E for the pull probably is the best answer. And then the second most popular answer is what could also happen, decrease. So if you don't have enough room in the column or any of the other inefficiencies, so that's good actually. The two most popular answers are what probably will happen. So for the sake of time, and I told you I wouldn't go, that's one idea, and I'll recap this, is you take your unit, you choose a common disturbance or a common set change, whatever it might be, and the key point is this transfer of knowledge, whether this is through your learning management system or whether this is just old-fashioned binder, it's getting that knowledge from and actually getting it on paper rather than just following someone around and kind of picking things up over 20 years from, people talking and things like this. Having some documented resources we found are helpful. Okay, so yeah, I'll just go through them, and if I can't see if there's questions, but that's okay. I will. Okay, yeah. So if there's any questions, we could also take those, but I think at the end, as Clay said, actually. So let me stick to the plan. Just one more full exercise we'll show you, and then we'll kind of recap the third. But this is something we've done for early career engineers, and it's really this troubleshooting methodology, and we call it Think Equipped. I'll let Don explain in just a moment here, but I do want to say that our goal, as I said in the beginning, is not to train your engineers how to troubleshoot like they were a process operator. It's more so that exposure level. And so anyway, I'll let Don explain this actually.
When you're in university, everything's kind of on an island, all the weather's perfect, and there's not a lot of things outside of the scope of what you're looking at. So if you're troubleshooting in the lab, you're basically going to have an equipment or an instrumentation problem. But we know in industry, these problems can reside in a lot of different parts of the plant. You're fed utilities, maybe the catalyst is starting to decay. People are involved, so an outside operator could have left a bypass in the wrong position. It does rain, you have winds, and of course you're involved in a big link of equipment. So you're getting your feed from someone else, and you're providing your products to someone else's their feed. So pressures and flows are getting impacted from upstream and downstream constantly. So when you have an upset, you have to really sense out in the beginning where that could possibly be, instead of just zooming in on something and overlooking where the problem really is.
Right. And I think, Don came up with this, and it's the ability to, we use the nice little acronym of QUIP for the categories, but just having these different categories about where should I look for troubleshooting, where are the inefficiencies in the system, and you could take this, and I'll provide the slides, but this same fishbone, you can make it custom to your unit. For our CAC cracker, for our fractionation, or our amine treating unit, you want to look at your feedstock, right? And here's the different things that are probably wrong. And it's just, again, one of these job aids where when we actually go through a style of exercise like this, that you could also do with historical trends, you could do it with past data, but really, and I can just show one real quick. I'll show it. The idea, again, for the engineer is not for them to come in and be super quick and solve it exactly and, change all the valving and things like that. But I think this style of exercise is rather good at least that awareness level of all the different things that could go wrong. When we're with operators, when we do an exercise like this, they'll give us 20 different things that could go wrong because they've seen 200 things that would go wrong. But basically the way it works and how this could work is I just put a fault in the program that will come in 15 seconds or so, right? And what will happen is all of a sudden, and I'll just call it out for time. Our temperature at the bottom, trying to keep everything at the temperature controller, so we only have to focus on one loop for the 3 demos. TIC 100 starts to drop, right? So we start to lose temperature in the system. And I'll just call it out real quick. So dark blue, temperature begins to drop. That's our PV. At the same time, my steam flow to the reboiler is going up. So that right there probably doesn't make too much sense right now unless it's a control response. we see that my level's building at the bottom, I'm losing purity, and I'm gaining flow at the bottom. So all signs are pointing that I'm at a cooler system. The only difference is right here, everything will settle out, besides I'll be using about 20% excess steam. And the idea is, using this sheet with those same different types of categories, could you come up with one thing per category or 5 different possibilities? Why on a distillation system? Again, not a critical error, let's say. We'll return all out of alarm. This will settle just a bit below. Why might you have to use an excess amount of steam on this unit? And this is one of those things where it could be 20 different things. And what we'll commonly see is, I'll just kind of go what we see from operators here, or if we're doing early career engineers, I have to be honest, this is one where operators will do better. But when you look at a system like this, if you have these categories, it can promote that thinking. Or to relate back to the first exercise, if an experienced operator could define different troubleshooting issues or different equipment to check using these categories, like it could have been fouling in the reboiler, steam quality. Quality is not as good, you need more steam. Faulty indicator, maybe you have higher feed flow into the column, instrumentation issues, so that's why you're using more steam, no problem at all. As always, people outside operator line up a wrong valve, whatever it might be, rainstorm, as Don kind of alluded to. So what we found is kind of outlining this, and then of course on the simulator you'd go through and actually find it. You go find the valve and you'd see a steam leak or something bigger than usual, let's say. But where we think there's value here, perhaps for yourselves, and again, we've seen people who've gone through the course done this on their own site, with or without us. The idea is, here's a screenshot right from a plant down in Chocolate Bayou. They took this same idea, and this is up in the control room, to kind of promote this discussion, where they just changed the categories. So they went materials, methods, measurement, manpower, machines, I believe that says down at the bottom. But the idea of what you could take is a simple fishbone diagram. We would suggest breaking it down by unit, include common troubleshooting areas, categories. And again, this is all just to bring early career engineers kind of out of the dark. Bring them in on these discussions, maybe just as spectators, so that they can begin to be exposed to the site-specific troubleshooting history. That's so important at forming this operations knowledge. So it's just another tactic that you can take, you're able to run with, and we believe there's value in there. And really, I think the biggest thing, Don, is that when we do a course for operators with this specific exercise, this sheet gets filled out in moments. They could list 100 different things, every piece of equipment that might be wrong. When we do a course for early career engineers, while they're very strong at this, just because they have the process background, they are not very strong at this. They just haven't seen enough. And does an engineer need to be able to troubleshoot like an operator? No. But if an engineer has at least a knowledge or an awareness of things that could go wrong, then to come to the next point, when we implement a new control scheme, when they are designing a new piece of equipment, they might have in the back of their head, oh, those guys always have trouble, with the thermocouples over here, So let me be aware of that when I'm coming in setting a new slate or whatever it might be. So I'll let Don take over for this this kind of third one here, but we think I can kind of just set up a second. I think when we said, okay, how can we help out here a bit with getting some operations knowledge for these early career engineers? And depending on the site we go to, the controls engineers and the operations team, it seems like the relationship's either great or it's really bad. And I think we've heard, it's not every site, but this idea of controls engineers coming up with a new control strategy, working with a vendor, getting a control strategy, really doing a really good job of diligence and understanding how it's going to implement it, the money it's going to save, the reliability it's going to increase, and then you go in the control room in 6 weeks and it's not being used. And I think the two main reasons for that could be twofold. I think the real one, based on discussions, is the lack of involvement of the operations team, or at least training or explanation to the operations team, which is general conversation between the controls engineers and the operators. So yes, it's going to respond differently. Yes, you're going to have to operate a bit differently. Here's what it's going to look like. Where the operator has one bad experience with it, and then they turn it off. And then there is always the case, the second, as I alluded to, is the control scheme simply makes things more complicated than it needs to be. But it's our belief, with a bit of operations consideration when implementing this, that your benefits will be kind of great here. So I'll let kind of Don explain this.
Okay, well, thank you, Matt.
Yeah,
Thanks.
sure.
All right, everyone. So we're going to look at this process control approach here, and there's different ways for us to control the tower temperature. We're going to look at the bottom control and how that's working. We actually have a cascade loop available at the top where we could take tower top temperature and throttle the amount of reflux coming in and out. But let's look at this right now. So there's a couple different approaches you could use to control that bottom temperature. You know, you could do it the old way, where you manually control that steam flow to the reboiler by just leaving TIC 100 in manual, and that has consequences, plus and minus. You could do the bottom temperature control as we do right now, under engaged, and that's sensing the temperature at the bottom of the tower and emitting more or less steam to maintain the temperature. Or you could take it to the next level and you could employ some advanced process control where you would actually make that analyzer a controller. So instead of AI 100, you could say AI 110, you can make it AIC 110 and have that controller directly resetting the amount of steam coming in and out by controlling the temperature. So the desired outcomes of bottom purity, choice 3 may be the best control technique, but it may be the least understandable to the operators involved. So I know when I first started in this business, the company I worked for, the founder was a controls engineer, and he had been introducing controls into companies like Dow and Union Carbide back then. And the issue was when they went out to the control room to see how the operators were doing with it, they were not doing well at all because they hadn't implemented it. They were afraid, they were more comfortable with what they had before. So as Matt had said, by developing some training, in this case, this gentleman created a simulator company to give operators a chance to practice and prove things out in advance so they would be more comfortable with it when they were working with it. So there's different approaches here to be considered here. So if you have a variability of feed composition, the feed stream varies quite a bit, will cause the steam flow to be more variable. So that's an issue that you'd have to be looking at. If you have bottom flow concerns, temperatures can swing, the bottom flow will vary widely, and this could cause swings in the preheater. And also you could have variability of bottom flow that could lead to instability in downstream units. So all these things would be trade-offs as you're working through these new ways to control the plant. You know, is this going to be a net positive? Hopefully, but there might be some differences along the way that could make some challenges. So while well thought out advanced process control typically leads to more reliable, it's very important for the engineers to explain the operations consequences of this new scheme to operators. And building that bond, as Matt said, is so key to having a well-run plant and a safe plant when those two teams coordinate with each other, respect each other, work well with each other, as opposed to have this adversarial relationship that's not helpful at all. So kind of race through some of this, but let's do some summary here and then open it up to some questions. So while recent engineering graduates have undergone a curriculum that focuses on problem solving and analytical thinking, there's not often a time for emphasis on process operations or process safety, and you really have that world scale obviously in a lab. You're also not able to get to a lot of pieces of equipment that are in very typical in a plant, like you're not working with furnaces, you're not working with turbines, you're not working with compressors. So, you know, you're not seeing a lot of the more complicated equipment in your unit operations lab. And of course, when you're out in the field, you know, refineries, dozens of furnaces, dozens of compressors, and so on. So this exposure to common equipment inefficiencies and process troubleshooting, they can help increase the confidence of earlier career engineers as well as improve the operator-engineer relationship. And we know that people want to do well in their jobs, but if they're not confident, it's going to show up and they're going to be tentative and not really be able to contribute as much as they could if they had this extra training. And the systematic approach to operations and troubleshooting can be implemented. And this important thing is to accelerate the time for engineers to gain an operations mindset, which otherwise you're going to take a lot of time, you know, in a very slow process in the field itself. So we think if you can boost this up kind of like a catalyst shot here, give this operations style training to engineers, there's going to be a lot of value in this and what they can do and help you in your plants. So we'll be interested in some chat if you have some comments on that, just to sound like it's worth it and sound like a good idea. So there's opportunities, of course, to learn more, and we have actually created a course, a 2-day course on fractionation/distillation operations for early career engineers that'll be happening next month. It'll be April 7th and 8th, and there's information here on how to sign it up. So it's something that we would encourage, if you're interested, to send an engineer or two to see if this is something that would make sense. And we could also conduct courses like this or in-house. Then we also have other training, virtual unit operations training and so on, that's simulation combined with self-paced e-learning, and that's available too. And then if you'd just like to keep informed on a more low-key basis, please click on that link and send Nancy McCarthy, who has reached out to a lot of you to sign up for this event, to join our newsletter mailing list, and we'll be sending out periodic updates and so on. So at this point, I think we have covered most of the items we wanted to cover in our formal presentation. So now we'd like to see if there's any questions. If you'd like to chat them out, Clay can relay those and be happy to hear what you have to say. And if you had any feedback on our presentation, that would be wonderful to hear too. So thank you so much for your participation and attention. We really appreciate it. We realize we have some people here are working off shift or not on our Eastern Coast time here in the U.S. So thank you for either staying up late or getting up early to be part of this. So with that, we'll end our formal presentation, and we'll see if you have any questions that you'd like answered. So thank you.
Yeah, thanks, Don. Thanks, Matt. I do have a few questions here that have come in, and we will have some time for a few more, so feel free to type those into the chat. The first question I got here asks, are there specific challenges in doing this type of training virtually versus in person?
Yes, well, we had that challenge last year when we were ready to get on an airplane and the trip got shut down. So it took some time to figure out how we would do this, and we used WebEx training, which is what we're using right now. So substituting for our in-class work where we would have flip charts and workbooks and walk around instructors and so on, we're actually able to duplicate most of that in a virtual environment. So when we conducted those courses, we were very careful to survey the people involved, and of course ourselves as instructors, we were challenged to see how this was going to work, but we're very confident it did work. We've done more of these courses. We have more customers signing up for these courses. So by thinking this through, being able to have installation of the software and checked out ahead of time, having each student with 2 monitors, so their simulator exercises were on one monitor and the instruction was coming through on the side monitor. That was one of the key differences that made things work. In some cases, there's been proctors in the room doing other work, but they're just in there to aid in classroom management. In one case, we had a room camera so we could see when the students were seated or were they getting up or back from breaks and so on. But the delivery was really good in terms of all the visuals were directly smack in front of the person's face on their screen. And with the polling and chatting and calling in and breakout rooms, we were really able to duplicate most of what we would do in person through a virtual course. So we're very happy with that product, and the feedback has been excellent.
Great. Let's see, next question here says, I'm coming from a university perspective. Let's see, let me paraphrase here, but coming from a university perspective, how does this approach differ in university than in industry, which is mostly what we discussed today?
Okay, so Matt's done a lot of work with chemical engineering universities. In fact, last year and this year, we conducted sort of a simulator Olympics. We call it Chemi Sports. So the students at these universities were signing up as teams, and we put on a competition where they were doing head-to-head competition in troubleshooting this distillation tower. So there were scenarios, there were new specs they had to maintain and so on. And at the end, what the students said is they were able to see all the pieces of their engineering education put into practice. So instead of having controls in a silo, design in a silo, and unit operations in a silo, this put it all together and in a fun kind of a way. So they were actually solving problems as teams that they were confronted with while still trying to keep the plant running safe and operating at a profit. So their scoring was based on safety, number of alarms and time on alarm, and also on how much profitability they were able to squeak out while confronting, loss of cooling, loss of steam, changing in feed quality, and so on. So it's there is a way to bridge what is traditionally a theoretical and actually put a little fun into it at the same time. So we've also done some of these Chemie sports internal to some universities, and then actually one of our industry clients who's a Petroskills Alliance member, OxyChem, we put on a competition internally for them where they had a bunch of young hire engineers going through similar exercises and having a little fun trying to maintain the column safety specs and so on. So I hope that answers that question, Clay.
All right. Next question. I got a couple different versions of this, basically asking if it's effective to include both operators and engineers at the same time in training with this methodology, and then if so, what are the pros and cons?
It's happened to us before because when we do courses, there's the class size is fixed for the course cost. So in some cases, plants want to take advantage of all the seats in the class, so they'll put a young engineer in. In those cases, those participants have kind of been very quiet. They haven't chosen to try and be the star of that show. They really are there to learn a lot. Or in other classes where it's just been engineers, this is more at some of the competitions and so on, there's a lot more free form. So while we can combine the classes, if it was ideal, I think it's better to have those two audiences, at least in the beginning courses, separated, just so they could be more free with their questions and so on. We have to gain the trust as instructors. Matt and I were in these classes, we're asking dozens, if not hundreds of questions. And to get an idea of what someone's thinking, we really have to provide a comfortable learning environment, and they have to be free to speak. So I think when we have those classes in separate, it's probably more ideal. But yes, we have done it where they have been combined. So if it's practical to combine them, we can do that. If it's ideal, we'd like them separate.
All right, makes sense. And then the last question I've got here, and unless anyone else puts any in the chat, is does this type of training work on systems other than distillation?
Absolutely. Yeah, so we show distillation as a relevant example, but yes, we have, smaller units, and we usually start our courses with something like a countercurrent heat exchanger to get people up on the methodology, the use of the simulator, and so on. Then you have pumps and valves, you have tanks, and then you have more like on the order of distillation furnaces, compressors, boilers even, turbines, and then we can get to larger scale units in refining. We can cover things like crew units, cokers, cat crackers, for midstream amine gas treating units and so on. So there's a lot of different variety of plants that we can offer in these classes as the basis of the process that we're studying. So absolutely.
All right. Well, that wraps it up. Thanks everybody for the questions. And Don, Matt, thanks so much for this information.
All right. Well, thank you, everyone. We hope we get a chance to see you again virtually or in person one day. So thank you so much for your attention and your support. Appreciate it.
All right. Thanks, Don. And as I mentioned, I will send out the recording of this to everyone along with the presentation, so you'll have access to some of those links and resources there. Thanks, everybody, for joining us. Take care and stay safe.
All right. Thanks. Bye-bye.